The Author Talk series is an initiative that celebrates ideas, inquiry, and intellectual exchange. This platform reflects Geo Institute's commitment to fostering a culture of curiosity and dialogue where distinguished authors share insights that challenge our thinking and enrich our understanding. We are truly honored to have with us today Dr. 𝗪𝗏 Subramaniam, former head of IBM Quantum India, a distinguished researcher, innovator, and author whose work stands at the forefront of artificial intelligence and quantum technologies. Dr. Subramaniam is embarking upon a journey to make India a leader in quantum computing. After his extremely successful leadership at IBM Quantum Mission, he will lead key initiatives at India's National Quantum Mission. Dr. Subramaniam holds a PhD in electronics from IIT Delhi, where he specialized in coding and information theory. For an illustrious career spanning more than 2 decades, he has made remarkable contributions to artificial intelligence, machine learning, natural language processing, knowledge graphs, and AI-driven decision-making systems. He has authored more than 150 scientific papers, holds multiple patents in AI and data science, and has served on the program committees of over 25 international conferences, including International Joint Conferences on AI and the International Conference on Data Engineering. Within IBM and across the global research community, Dr. Subramaniam is recognized as a leader who bridges the gap between advanced research and practical enterprise applications. Today's talk is centered around his recent highly acclaimed book, Quantum Nation, India's Leap into the Future, which outlines India's strategic imperatives to leadership in quantum technologies. In this work, Dr. Subramaniam presents a visionary roadmap for how India can harness the power of quantum computing, not just as a technological revolution, but as a strategic national endeavor that positions the country as a global leader in this transformative field. It aligns perfectly with India's ambitious vision under the National Quantum Mission, a transformative step towards global leadership in quantum technology. We look forward to gaining insights from his vast experience both as a scientist and as a thought leader, shaping India's journey in the quantum era. Friends, please join me in welcoming Dr. 𝗪𝗏 Subramaniam to join us.
Camera becomes more powerful, the apps become more powerful. So all of this, and that's been the Moore's law, right? Moore's law, making compute power double every 2 years. But in spite of all this, what are the limitations of computing today? Okay, so let's take one simple example. We all know caffeine. It's there in coffee, it's there in cold drinks, all of that. Now let us say this coffee molecule, you wanted to model it for 1 fraction of a second. Where are the atoms? Where are the electrons? For 1 fraction of a second. All you want to do is model that for 1 fraction of a second. Now, if you wanted to do that on a supercomputer, we can go to the next slide, or if it's working, I can take it. Yeah, thanks. So to do that, you would need 10 to the power 48 bits. 10 to the power 48 bits is 1/10 the number of atoms which are present on Earth. Are we going to ever build a supercomputer that big? I don't think so. It's never going to happen. And that's where quantum computers come in. With 160 qubits, quantum computers can model where the atoms are present in a given molecule. Now, why is this important? Why is molecular simulation important? Anybody? Do you know what is medicine? What is a medicine? A medicine, in our body there are 25,000, 30,000 proteins. Proteins have 3-dimensional shape. One protein looks like this. Another protein looks like this. Another protein looks like this. Multiple shapes. You know coronavirus? Shaped like this with spikes. In the lungs, there was this receptor. When that happened, what happened? COVID-19 happened. And what is a medicine? A medicine is a blocker that does not let coronavirus to come and sit like this. What is cancer? A protein in our body which is like this becomes like this. That's cancer. That's diabetes. That's proteins in your body losing their shape. Okay. What is medicine? Protein which has lost shape. That's medicine. Now, to find this molecule, medicines are molecules. We just saw that you cannot simulate molecules on supercomputers. So today, how do we make medicines? In one test tube, you take disease. In one test tube, you take molecule. You pour. You observe. You think it's working, then you take it to rat, dog, human. Okay, when finally you take it to AIIMS, 25 people with disease, 25 without disease, and you observe. Did it work? If it worked, then you say, okay, good medicine, I will start using it. If it does not work, you go back to your test tube. Again, rat, monkey, dog, human. And remember, there are molecules, there are proteins in your body. One is shaped like this, another could be shaped like this, and this medicine could come and affect that other protein also. What is that? That is side effect. For a disease like cancer, you will say, "Achha, koi baat nahi. I will live with this side effect." But for the other diseases like cold, you say that, oh, I don't want any side effects for cold, common cold. So, medicines from 5 to 10 years today, you're going to accelerate it to much faster things. Not only medicines, any new materials, plastic. We all want a replacement for plastic. New material, molecule. ISRO wants new materials for space, which you can send to space, lighter material, less fuel, but strong enough to withstand the radiation, the heat, the cold, all of those things. New material for agriculture. What is fertilizer? Fertilizer is nitrogen in the air. Take it and put it into the soil. But it is one of the most polluting industries today, fertilizers. But we can't live without fertilizers. Why? Because 8 billion Earth population, if you don't use fertilizers, you can only grow food for 4 billion. Only because you have pesticides, you have fertilizers, you are able to grow food for 8 billion people. But it has side effects, it has pollution. So how do you change that? New materials. Today, new materials take 10, 20, 30 years. Some of you might remember plastic was not very prevalent 20, 30 years ago because that was a new material at that time. Today, we are sick of plastic, we want to replace it. So we are looking for newer materials for replacing plastic. Electric vehicles, new battery materials. Can we move away from the rare earths? Can we find new materials where your car is able to run longer distances using the batteries? All of these are new materials where you need molecular simulation. And as we saw, you cannot do molecular simulation using classical computers. You need to do only wet lab physical experiments, and that's something quantum is likely to change. So we saw one example of something which will get changed because of quantum computers. new materials, molecular simulation. What is the other one? So we all use encryption, passwords. Do you know what is a password? What are prime numbers? Prime numbers are numbers which can only divide themselves or by 1, right? What are the prime factors of 15? 3 into 5. Prime factors of 100? 2 into 5 into 2 into 5. What are the prime factors of 1, 2, 7, 9, 8, 2, 5, 6? A very large number. 2048-bit integer, the best supercomputer will take 8 billion years to prime factorize it. So what do we do today? You take a large prime number, I take a large prime number, we multiply it, and that's our key. So all your banking transactions, all your passwords, if this is getting broadcast, even if somebody is catching the signals, they can't break into it unless they have the Zoom password or something, right? All of that, why do we do it? Because prime factorization is something classical computers will take billions of years. Now in 1994, Peter Shor showed that a quantum computer can break this factorization 8 billion years in 6 hours. Done on a quantum computer. So exponential speed up. So we just saw two problems. One is molecular simulation, which you will never be able to do on a classical computer. Second one, factorization, which you can do on a classical computer, but it will take longer than the life of Earth. So you need a quantum computer there. What is the third problem? What is AI? What's AI? AI is learning. Today's AI is all about giving lots of examples and it learns from that. It builds a model and it says, here, I've built a model for this data and I can use this data to make inferences. So, one such example, cat. As a child, how many cats did you have to see before you said, Mama, Billy? Two, three, right? Maximum 2, 3. Then you said guy, share, everything, right? 2, 3 examples. Each one of them needed 2, 3 examples for you, right? Today's AI, how many examples does an AI system need for the cat? 10,000 or more. Cat from this angle, cat from this angle, occluded cat. And still, you show a cat, you show a cake which is shaped like a cat, AI will say Billy. But your son or daughter, 2 years old, whom you have shown only 1 Billy in their life, will never call the cake a Billy. It will say Billy wala cake or something like that. It's not going to say Billy. No. What is the problem? The problem is in the data representation and the inferencing. And so, what is happening today? Every time you build one LLM, what do you build on the other side? A power station. So all the tech companies today are buying nuclear power stations to run their AI models because of cat problem. The same cat, you do your inferencing, you eat 2 rotis and you're done. That's your power requirement. AI, on the other hand, requires lots and lots of electricity just for that cat problem. So Donald Trump, on January 20th, the day he took over, the first thing he did was he declared a energy emergency in the US. What is that? That is to say that all our AI and all of that, we need lots and lots and lots of power. And so I declare an energy emergency starting today. And that's because they're planning for that AI future where you're going to require even more and more and more power. There are models which show that if we continue at this rate, by the year 2027, 2 years from now, the earth is going to be filled with power stations. And that's where quantum comes in. 2 billies human, 10,000 billies AI of today. And quantum, we are seeing evidence that it's getting closer to the human. Not 2 billies, maybe 20, maybe 200, but not 20,000 either. So we just saw 3 problems, right? One was simulating nature, molecular simulation. The second was a mathematical problem, which is factorization. And the third one is AI, where in each one of these, quantum is able to do things which classical is not able to do. Okay. But does that mean that quantum is going to replace today's classical computers? Yes? No?
Yes. No.
Yes? No? Okay. We'll come to the answer for that. But what is it that quantum does which is different? So the difference is in your way in which the basic unit of information on your laptop, on your mobile phone is bits, zeros and ones. You write a program in Python, Java, C, C++, there is a compiler. That compiler does what? It converts it into a string of zeros and ones, and that conversion is then passed on to the processor, and that processor takes those string of zeros and ones, does the processing, gives you back the results. Okay. So your programming is in higher level language. Higher level language is like English. For 1 to 100, do this. That's what you would do in your program. C, C++, Java, Python, all of them. That gets converted into a string of zeros and ones which runs on your processor. On a quantum computer, does what changes? Does the programming language change? No. Same programming language. You use your Python, C, write your program. What changes is that compiler. That compiler is going not to convert it into a string of zeros and ones, but it's now going to convert it into a string of qubits. What are qubits? Okay, you have to look this up, but it has 3 special properties. One is superposition. What is superposition? Your bit can be only 0 or 1 at any given point of time, whereas a qubit can be both 0 and 1 simultaneously. 2 qubits cannot be connected, but 2 bits cannot be connected. They will always be independent. But qubits can be connected. Multiple qubits can be connected together, and they will simultaneously share information. Okay. Now, if you remember Einstein said things like, God does not play dice with the universe, spooky action at a distance. All of these were words Einstein used to describe quantum mechanics. He never believed in these properties. Okay, these properties, but of course now, and he asked a lot of questions which took 50, 60, 70 years for scientists to answer. And now we know that, these are possible things in quantum mechanics. Small objects have these properties. And that's what quantum computers today are exploiting. So for the first time in the history of computing, what has happened is computing has branched. There are two kinds of computers today. One is your laptop, supercomputer, mobile phone. What is there in these? Zeros and ones. Unit of information is 0 and 1. The quantum computer is a new kind of computer, very different. It is not an extension of your classical computer. It's an entirely new kind of computer, and that's why for the first time in history you have two branches of computers. The classical computers and the quantum computers. Now I asked you if quantum computers will replace classical computers. No, they will not replace them, because classical computers are very good at things like multiplication, things like, okay, sorry, things like some
Done?
okay.
Done.
But this has moved to this mode. Yeah. Okay. So the future is where quantum and classical computers will work together. Okay, so you're not going to be able to replace any of them. Both of them are going to work together. And okay, perfect. So in future you're going to have CPUs, GPUs, and QPUs working together. So that's the future. Okay. And already we see that on your laptop you have mostly CPUs, on your mobile phone mostly you have CPUs, but you are already using a lot of AI programs like ChatGPT, which goes to the GPU and gets the answer from there, right? So it's already happening. Very few laptops have GPU. But similarly, QPUs are also sitting in the data centers. Okay, so there is now, already you can use quantum computers for free. Sitting here, you can access a quantum computer, just type quantum computer access, and you can access for free quantum computers from IBM, from many others. You can actually run your program on a real quantum computer right now. Okay, so that's something you should do. And quantum computers are also following a Moore's law like growth. Okay, so 2016 5 qubits, 2025 156 qubits, 2033 1 lakh qubits. So again, exponential growth is happening in the quantum computer hardware space. Okay, and all of that is pointing us to a point where what we call quantum advantage. What is quantum advantage? Which year did PCs come? Anybody remember when were PCs? Apple PC, I think they were called microcomputers or something on the desktop. So they came in the 1970s, mid-70s, okay. The first desktop computers came in the 1970s. But do you know who and when PCs became useful? Who made them useful?
IBM PC, I remember.
1981.
Yeah. Around 82. It came to India around 82, 83.
82, 83. Yes, very true. But there was one company which made PCs useful. Microsoft. Through their operating system, and tools like Excel, Word, and all of these. Okay. Before that, PCs were sitting inside labs. Nobody was buying a PC. PCs came to our desktops only after Microsoft created operating system. Which year did World Wide Web come?
95.
83, okay, 1983. But which companies made internet useful?
Cisco. Yahoo. Netscape.
Yeah, very good. People here know all the answers. Okay, so many of you are very young. You might not know about Netscape, but somebody mentioned Netscape. Before Netscape, there was no browser. Can you imagine going to a website without a browser? Go to your computer today and try to go to a website without using the browser. Before Netscape, we did not know how to go to websites. The second one was Yahoo, Google. Google brought automation there. There was data everywhere, but we didn't know how to search it out. If I wanted to go to the Geo Institute website, I would have to call one of you and say, "Batao, address batao." And I will type Geo Institute dot whatever. Today what do? I go to Google. But before the late 90s, these two weren't there. I did not know how to go to a website before that. So what would people do? They would buy PCs to play games, to do word processing and everything. But they would say, "Acha, internet ka kya karunga main? I don't need internet." It was only after Netscape and Google that people started using the internet because they found it useful. Okay. And then, of course, Geo came and changed everything. Made internet connection so cheap in India that all of us now, you can't imagine living without internet. Right? So, there was hardware. World Wide Web was existing, but somebody had to come and make it useful. And that was Netscape and Google. AI. Which year was AI invented?
40s.
Yeah, 1950, that Turing test and all those things came. But yes, you're right. Even before that, people started talking about AI, expert systems and all those things. But who made AI useful?
ChatGPT.
Yes. Before ChatGPT, AI was, some professors were using, it was sitting in the labs. Now, I don't know anyone who doesn't use AI. Everyone uses AI now. So, and before ChatGPT, what was NVIDIA? A normal tech company, like any other tech company. After ChatGPT, what was NVIDIA? The most valuable company in the world. So it was the use case which made it that same NVIDIA chip, no difference. But it was the use case. So what is quantum advantage? Quantum computers are sitting in the lab. Who's going to create that use case that brings the quantum computer outside the lab and makes it useful? And that's called quantum advantage. Who's going to bring quantum advantage and when is it going to happen? Who's going to bring quantum advantage? Some guess. Okay, so let's try to answer this question. Where is the maximum talent for quantum computing today? It's sitting in India. The maximum talent for quantum computing sits in India. Okay. You see that on the IBM quantum computers. I told you they're available for free. You can go and use them. Who's using them? Indians. This is a McKinsey report. EU is a collection of multiple countries. India is the largest country there. So, we offered a course on NPTEL. You might know about NPTEL, right? 15,000 students registered, out of which 7,500 were 12th class students. Unheard of. That students in 12th class, no, quantum computing is not even there in their syllabus. They don't have to study it. But why did half the number of people who registered were 12th class students? Why? We don't know. Okay. Yesterday we launched a program for 50,000 students in Andhra Pradesh. 50,000 students, 1 month program taught by Nobel laureates, launched in Andhra Pradesh. 50,000. And we expect to cross that 50,000 very quickly. It will start on December 8th, 1 month program. And we are expecting that, seeing the groundswell of interest, that we will reach that 50,000 and cross it also. Okay. So something very special is happening in India. Okay. So if the talent is sitting here, where should quantum advantage come from? Yes. It has to come out of India. That Microsoft or that Google or whatever of this decade has to come out of India. And to do that, there is something called the National Quantum Mission, where the government is spending about 6,000 crores. And currently, those 6,000 crores have been distributed among these 43 institutions. Okay. So many, and this is just the first round. Okay, there'll be others in the next rounds. There was a call for quantum algorithms also. So the 6,000 crores is getting distributed to say that, look, come up with a big idea. Here is a basket of money. Come with a big idea, take the money and make us reach quantum advantage. That's the goal. And if the profs are slow, there is also the startup program. They're giving up to 25 crores to each startup. And that's just the beginning. There is more money where that came from. Okay. So the point now is, can you think of those big ideas, big problems? Can you aim high and solve them? Okay, so that's the goal here. To reach quantum advantage before the rest of the world does it. It has to come out of here. In the past, any technology, you take any technology, okay, you take, we keep talking semiconductors, father of Pentium, Venkata, Indian, studied in one of the IITs, went to US, okay. Father of fiber optics, Kapani, Indian, studied in India, went there. We have always been great at talent. There was no technology where India did not have the talent. There was no technology. In the past 30, 40 years, you pick a technology and Indians were the leading people creating that. And that shows today. You look at the CEOs of IBM, Google, Microsoft, they're all Indians. So talent has always been great, but as a country, we have not fully benefited from that talent. We haven't made use of that talent because Microsoft was not an Indian company. Whichever others were not Indian companies. They had talent from India, great. But they were not Indian companies contributing to the Indian economy. So now what is that change we can drive is we need quantum advantage to come out of India from the Indian companies, okay? And that's where you can drive that change. And that's where, there is money now, there is intent. All of that is there. You need to start thinking big. Okay, so that's what you really have to do at this point of time, right? So from the government point of view, they've started education programs, they've started startup programs, they've started funding professors and several other academicians. They have started programs where jobs are getting created. So today, if you see in quantum plus AI, I don't know if you know, there is this bank HSBC. HSBC and IBM showed that in algorithmic trading, if you use quantum plus classical, you get a 34% jump in the prediction for algorithmic trading. The day this was announced, what happened? IBM stock went up 6% or something. HSBC stock went up. Every bank started calling. हमें भी बताओ. We also want to do this. Give us a roadmap. Now you are sitting at the center of India's financial industry. This is a great opportunity for you to take the lead, take that HSBC result, implement it in using AI and quantum. And today I can tell you, finance jobs are the most sought after. I live on IIT Delhi campus. Every kid there wants to land a financial job because those are the 1 crore plus packages, right? All those companies, of course, want AI and statistics and maths, but they are also looking for kids who know what is quantum and they can create that roadmap for themselves, in their companies. So, and this is not just the foreign banks. This is Indian banks, Axis Bank. You go look it up. Axis Bank Quantum. They have started their quantum journey. You look at 𝗏𝗂𝘂, Gift City. They have started funding quantum startups and all of those. Okay. So there is a great opportunity ahead of us across sectors. Molecular simulation can apply to pharmaceuticals. It can apply to petrochemicals, it can apply to mining, it can apply to the Reliance Industries, several of the group companies. Directly, you can apply it. AI plus quantum. Okay. So here is an opportunity for each one of you. You're living in a time where many people say, AI is a disruptor, it will take away jobs. Yes, it will take away jobs. In IBM, 8,000 HR people gone, replaced by HR-GPT. Marketing jobs gone, replaced by marketing GPT. CIO office jobs gone, replaced by CIO GPT. But at the same time, there are multiple new jobs opening up. There is a saying which was there in my old office, which said that people who know how to use AI will replace people who don't know how to use AI. It's not AI which will replace people. It is people who know how to use AI who will replace those who do not know how to use AI. That's what's happening today. And for a country like India, AI is a big opportunity because I know only Gujarati, I know only Marathi. AI is going to remove that language barrier completely. I can work from here for the Koreans, for the Japanese. I can build apps for them because AI can give me that opportunity which I did not have. Today all of us use ChatGPT as our assistant. And that is going to expand to everything. You might have heard about agentic AI. So it's already happening. AI agents are coming to help us across sectors, across areas. And it's now for us to see how we can use that, combine technologies like cloud, quantum, space, everything, put it together and solve problems that are there in the domain. Okay. So I will stop here. It's been a pleasure. I had many things to cover, but thank you so much. Yeah.
Do we have any questions?
other than the compute level changes, a fastening of compute level changes, what would quantum algorithms bring into table? Something new that, for example, similar to, like you told the cat as an example, far similar representations, far fewer representations, like that, any other cases that it can bring into table so that...
Yeah. So, see, on our classical computers, we are doing many things, data science, AI, optimization, and all of these things we are already doing, right? We are doing these things. I'll give you an example. You know, DRDO lab, 𝗏𝗏, they build models for torpedoes, submarines, and ships. Maruti has a wind tunnel. New car design, run it through the wind tunnel, you measure. Okay, then you say, अच्छा ऐसे नहीं, ऐसे कर दो उसको थोड़ा. Okay, so that's what wind tunnels are for. It does the fluid dynamics of how the air flows around you to get to that right design and all those things. Now underwater, what do you do? Underwater, yes, Cochin has an underwater range, but you can't test everything there. You can't, unlike the Maruti cars are always shaped like this. They go at a certain speed. There is a speed limit. All those things are there. But torpedoes, submarines, ships, to model 1 cubic centimeter on the best supercomputer today takes several hours. Imagine this much space. How are you going to model that for the torpedo? Yes, you can build algorithms to run on the supercomputer, HPC, all those things, but still it will take you days and months and all that, right? So what does the quantum computer bring? It brings you now a new opportunity to look at a new algorithm which is going to exploit those superposition, entanglement and interference to try and solve this problem. Okay, so just like AI, molecular simulation, drug discovery, okay, that brings us to one more slide which I want to, okay, it's not going. Yeah, so there are multiple sectors, you know, like finance, aerospace. In each one of them, people have begun looking at multiple ways in which you can, exactly what you said, which is that problem where I can start solving, okay? And as a country, we are trying to define at least 100 such problems where we are able to say that here, take these 100 and try and solve on a quantum computer. Here is data, benchmark it against the best classical, and using that, try and solve it. Yeah, just go one or two more slides forward, more. So every state is now, this one, okay. So this one has multiple sectors where people are trying to solve different problems by developing new quantum algorithms. Yeah.
So I have a slightly contrarian view, and do you have a more realistic roadmap on when do you benchmark yourself and say that quantum computing has succeeded or there is a realistic product out there? Because I mean, as academicians, we're always taught to be skeptical, right? Mm-hmm. It's the same thing that there is so much hype about, like when do we say it's just an irrational hype versus something real, and how will you, what benchmarks will you use to define, what are the metrics for success and all?
Yeah. So see, quantum advantage has a very rigorous definition, okay? So you should just Google it up, okay? How do I say I have reached quantum advantage, okay? So that rigor is basically to say that, for example, you take Shor's algorithm, you do factorization, okay? So what is Shor's algorithm? It has shown exponential speed up, okay? It has shown it. Mathematically, you know that I can do factorization exponentially faster on a quantum computer. So on a mathematical level or on an algorithmic level, it is proven, right? You can, there are very rigorous proofs that you can give that that speed up is actually happening. Now, do you have a quantum computer which can run that algorithm today? You don't have. Okay. You don't have Shor's algorithm is there, but you don't have a quantum computer powerful enough to run that. I mean, you can run it, but for small numbers. You can't run it for that 2048-bit integer which I told you about, because you need thousands and thousands of qubits for that. Okay. Do we have that number of qubits? No, I told you there is this plan ki 5 se shuru hua, 2016 mein 2033 100,000 qubits will be reached. Now, using the 120 qubits of today, we know we can't solve Shor's algorithm. But what is that algorithm you can solve? Okay, and that is what is quantum advantage, to be able to say that today's quantum computer, I will use the 120 qubits that you are giving me to solve this problem. Okay, so to solve that problem, there are people. So for example, Microsoft recently claimed quantum advantage on a problem where they said, some random sampling problem, where they said you run this on a classical computer and you run this on a quantum computer, there is a 10,000x or some such number speed up. And they proved it. Okay, they showed it. Now of course, what will also happen is the classical guys will say, "Acha, ye karke dikhaya tumne quantum mein. Let me show you what can be done on a classical." So the next few years, you are going to see quantum claim something. Then the classical guys come and say that, "Okay, I'm going to show you. I'm going to run this on a quantum computer faster than that." So both these fields will keep going up on certain problems like molecular simulation. Tomorrow you might say that, "Oh, I have this problem. I'm solving this ML problem on quantum computer." Somebody from that side will say, "Okay, I'll solve the same thing on a GPU." Okay, that is going to continue, but the metrics for that are already in place to a large extent, not fully. Okay, and today, if you see many of the Nature papers, they will pick one molecule, they will simulate it on a quantum computer, and they will say it's not doable on a classical. Then tomorrow somebody comes and says, "Okay, I'll show you on a classical." They might or might not succeed. So the next few years is going to be this race between the two. And then there will come a point when quantum will break away, which is exactly what happened with AI, for example. You said there are problems that AI cannot solve or things it cannot do. In the mid 2010s and all, 2015, 2016, people said for AI to do sentiment will take 100 years. I mean, there were many people saying multiple things. Aaj you go and ask ChatGPT for a joke or a sad this thing, it will give it to you. So, I mean, I don't know how I answer.
My question was, what is the realistic timeline you have in mind? Realistic timeline.
The realistic timeline from IBM is 2026 for quantum advantage.
I have a question. Actually, I'm reading your book right now, Quantum Nation.
Yes, sir.
And I find many parts relatable because I grew with the Indian IT industry, so I'm able to relate to that. At one point you mentioned how Einstein wrote to Niels Bohr and Heisenberg, where he criticized this theory of entanglement and superimposition, and they responded back. And there was a lot of back and forth dialogue that happened, debate that happened, discussion that happened, which actually created this quantum mechanics forward. It really gave a big impetus.
Correct.
In Indian university systems today, this culture of debate, dialogue, discussion is unfortunately missing and reducing, maybe more, because I've seen the older university systems as well.
Yeah.
And no amount of courses, no amount of hardware, software, networking, all those stuff will be able to make India a quantum nation if we don't address this issue of culture of dialogue, debate, and providing critiques. What do you feel about that, sir?
Yes, sir. So that's a very important and valid question, and which also brings back your question, where how do you say that something has been achieved or not achieved? And that's a debate, like you said. Because the quantum people will say something, the classical people will say, no, that's not true. I'm going to show you better things. And unfortunately, you're right. That debate is not happening, not happening sufficiently. And hopefully the National Quantum Mission will create that debate, and it will also bring people out of that, so one big change which I see now versus even 5 years ago, there was something called the Nano Mission in India, Nano Mission, some people call it successful, some people say it was not successful. Lot of research papers came out of it, but no industry came out of it. So this time, the National Quantum Mission is saying, paper chhapte raho, koi baat nahi. But we want technology to come out of this. So their whole mentality has changed, And I believe, the dialogue only comes when you move out of those 2%, 3% to that hard engineering where you are actually answering the questions that sir raised there, saying that, when have I reached quantum advantage? Show me, show me the proof. That's really an engineering task. There is, of course, a lot of science behind it, but it's going to be some kid like Bill Gates who's going to create that operating system and say, look, I've done it. There's nothing deep science about it, that operating system. It is about taking a piece of technology and making it usable. You look at Google, just one chota dabba, that's all. Anybody can use it, very simple. So we need to make technology simple, and that only happens through dialogue, and not only dialogue between professors, but also dialogue between the end users, the farmer, the rickshawala, or whoever who is going to actually benefit from, because otherwise it's of no use. That technology doesn't go anywhere. Yes, sir.
Thank you very much for this great exposition on Monday morning. Really appreciate. My name is Anirudh, Professor, and I have a simple question. How does quantum computing impact student learning in the classroom? And what can universities do today to harness that advantage?
Yeah, so quantum has brought a lot of excitement. That's one thing. I go to multiple colleges and I see kids very excited about quantum. And it also, I've covered a little bit in the book, it also relates to many of our Hindu learnings, saying that the universe has multiple, things and all of, and if you look at the early atomic scientists and all, they also used to read the Gita, quote it, all of them were doing that. So what I'm seeing is that students have a natural inclination towards it, but we make it very theoretical. That's a big problem. Let's not, kids today want to touch and feel, because that era of just reading has gone, because you need to use that learning to build something. So I think that excitement is what we have to bring through small, it could be double slit experiment, whatever, or even a simulation of that on your laptop, But we need to make it real, people seeing it, touching it, feeling it. And that's what will bring new ideas for the 20-year-olds to come and make the new Microsoft or the Google of the world. Ma'am had a question here. Sorry, just before I come to you.
There are a few participants online who have sent their questions. So can we achieve quantum advantage now with gate-based or quantum annealer? I am trying with a vehicle routing program. Can you please kindly provide some insights?
Yeah, vehicle routing is a beautiful optimization problem, where and optimization is everywhere, even in your class scheduling, exam scheduling, hostel room scheduling, all of that is an optimization problem. Okay, so this vehicle routing is one such problem. You know, airports face this. You know, yesterday I landed in Mumbai airport, flight had been delayed, and that's primarily a routing problem. You know, it's about having 20 gates, 30 aircraft, 40 pilots, 20 stewardesses. How do you manage all these at the right time? So for this, you know, rightly the person pointed out there are two kinds of quantum computers. There is one which is called an annealing based quantum computer, which is only for optimization problems. Okay, so you give it an optimization problem, it comes to the minimum energy state in a natural fashion there. Okay, which is what a vehicle routing problem is all about. The second is the gate-based computers, which is the IBM, Google, and all of these, which are called universal quantum computers, because they not only solve optimization, but they also solve things like machine learning. They also can solve things like molecular simulation, all of those. So both of these are computers which people are using. And for example, you know, the HSBC problem or the Axis Bank problem, people have shown using real data that they have attained some advantage in these things. So to the person asking, I would suggest that, you know, look at, of course, QAOA, which is one of the ways in which people model these things, but also see how you can go beyond it, how you can do approximations for larger systems, because when you go beyond a number of vehicles or routes, you have to many variables, it blows up, exponential blow up happens, right? So, and work with real data. Those are the three advices that I would give this person. And yes, sir, yeah.
Like when we say quantum advantage, we are using QRNG and QKD. So QRNG is far bit accessible over APIs and all. How do you see that QKD is feasible to use cases? Like QRNG is now used POCs and other things.
Yeah.
QKD is something which is not reachable, or how you see when it can be available for industry use.
So QKD, you know, so the government of India has created 4 hubs. Okay, one of them is for quantum communications, IIT Madras and C.Delhi. Okay, so these people are using QKD. Okay, the factorization problem which I told you about, where you are taking prime factorization and using that for encryption, that needs to be replaced because quantum computers will break it. So there are 2 techniques. One is called QKD, which you just mentioned, quantum key distribution, where the keys themselves are quantum. The other is the keys are classical, just like prime numbers are classical things. They are not quantum things. So instead of prime numbers, you are now picking it out of a lattice. Okay. So there are 2 methods, PQC and QKD. Okay. And QKD, you're right. There are multiple issues there. You might have heard about the China Mauritius satellite. I just visited last week ISRO labs, and they are actually putting together India's satellite there, the quantum satellite. Okay, so you're right, multiple things have to happen for QKD to succeed, including entanglement at a distance. Many of those things haven't been shown, and in fact the bit rate becomes so small that you can't do much using QKD at this point of time. But yes, these are all beautiful, nice research problems which we need to solve before we can get there. But you're right, many exciting things are happening which need to solve this QKD problem at scale.
We need industrial use cases.
Yes.
More accessible like chat.
Correct. So the first use cases are of course defense, space, maybe banking, all of these. But for it to come to internet scale, there is a lot of breakthroughs have to happen, as you said. Yes, sir.
I also have a technical question from experimental side of things. I myself is involved with the NQM in the materials and devices vertical.
Oh, very nice.
I work on spin qubits. But there is this divide that there are these groups working on superconducting qubits like IBM itself, silicon spin qubits, there are neutral atoms and photonic qubit chips. It seems there is a divide, and we are still not sure which one is going to be the right qubit platform. What do you think is that one killing experiment where we can say like unequivocally that this is the right qubit platform to make it grow like a Moore's law? Or do you think that different applications will require different qubit platforms? Or
Yeah, and that's a question I don't have an answer to, but I will put some thoughts here. So spin qubits use semiconductor technology. Okay, so people really want spin qubits to succeed because what happens?
scalability.
Scalability. You can keep producing qubits just like you are producing transistors today. Okay, so but spin qubits so far haven't succeeded in building out a scalable platform at this point, right? The platform which are succeeding are two. One is superconducting, which is what IBM and Google are going after, which uses what is called a Josephson junction to create these superconducting electrons which will do the tunneling. Basically, it's all about creating those properties, superposition, entanglement in those qubits, right? So qubits can be made out of light. Single photons are also qubits. Qubits can be made out of atoms. Qubits can be made out of molecules. Qubits can be made out of electrons. And as Sir pointed out, there are multiple ways in which people are trying to do this. Okay, so spin qubits is one of the techniques India is trying. Okay, including superconducting, many of the ones. The simple answer is whichever is able to scale and show quantum advantage will be the winning one, right, in the beginning. But also remember, for example, your today's technology, semiconductor, the processor uses one technology, the memory uses another. So even inside here, and 5 countries control the supply chain today. South Korea, Japan, Taiwan, China, US. 5 countries. Each one of them specializes in some parts of this. Each one of them uses different technology. Okay. So even though we say semiconductor, all of them are different deposition, different kinds of techniques. Okay.
Logic and NAND.
Yes, exactly. So all of them are different. Okay. So even in quantum, we don't know. Okay. And even in semiconductors, remember before silicon was what? Germanium. So even the material we don't know. Today it's aluminium, tomorrow it could be cobalt, it could be diamond. I don't know which one it is. Okay. And yes, you're right. We still have some distance to go. And that's what National Quantum Mission is saying. Please get started, get going, try and solve these problems, and then we'll figure it out. And that's what you have to do. You need to do, as a materials person, you need to create that, path for us. And remember, even fabs, there aren't too many in the world where you can go and try out these things, In the world there aren't. In India we don't have even one at this point of time. So these are things we need to create. As we go forward, these are things which if we create today, tomorrow we can be the leaders.
I think we'll have one last question of the day, which is from an online.
There's a 2-part question from 𝗏𝗪𝗀. He says, thank you for the informative lecture. Could you please throw some more light on the AI molecular simulation drug discovery trial? And second part is, what novel physics, material, science intervention are necessary to create a robust qubit?
Very tough questions. So you all know what was last year's Nobel Prize in Physics? It was to AI. Last year, not this year. This year it was for quantum. Last year's AI
Hinton, no?
Yes, Hinton. Okay. So Hinton and those other guys. Okay.
Yeah.
So that was the physics prize. But many people don't know that the chemistry Nobel Prize last year was also for AI. It was for protein folding. Proteins. Okay. So to answer this person, there is already a lot of work which people are doing in these areas for molecular simulation, for drug discovery and all of that, where AI is also making big impact. Okay. First AI Nobel Prize, and this is not going to be the end. And the future, you will also now start seeing that AI requires a lot of examples, right? We saw that. Cat problem, lot of examples. So there are many unseen proteins in our body. AI hasn't seen them. So how does it predict anything? And that's where quantum comes in, where quantum is able to predict things where you don't even have examples, which AI needs. AI needs examples to learn from. Quantum often doesn't need those examples because it's using the same principles to create that simulation, right? So the answer to this question is that, yes, we are going to find more and more of these molecular simulation, all these protein folding, where AI and quantum are going to come together. Remember, CPU, GPU and QPU working together to solve these multiple problems. The second one was about qubits. What is the right material? And that again comes back to the question that sir asked. Today there are multiple competing technologies. Light is one, atoms are another, molecules are another. And the clear winner hasn't yet emerged, whether in terms of the materials, whether in terms of the qubit modalities, whether in terms of creating those qubits in a scalable manner. None of that has happened. Light, for example, how do you scale to thousands of qubits with light? How many lasers? How many, photons? How big is that system going to be? And that's why spin qubits is a beautiful one. Just pack it into your semiconductor, which we know how to do. But that's not working today. It's not scaling. So there are many tough questions for which many of us, many answers are not even known. But I think just asking those questions is important, because as sir said, that dialogue is important. We need to get into that dialogue and start solving some of these problems.
Of your talk is more on an audience. First, I would like to know about the NQM itself. It was conceptualized let's say 2-3 years back. The proposals came in, the hubs have been set up. How is it all evolving when you compare it to global efforts, let's say in China, US and Europe? Not just in terms of ambition, it's a very ambitious project that the GOI has taken up, but on ground progress, how is it evolving in your eyes?
And before I answer, this view here, people online can't see it, but I can't take my eyes off that, so it's very beautiful sitting here seeing this, it's one of the most beautiful rooms I've ever been to. Okay, so nice. So NQM, as sir said, it's a very ambitious project. Okay, 6,000 crores. And that's just seed money. Remember, आपके पास idea है तो there is more money for beyond that also. Okay. And a lot of this is for creating infrastructure which we don't even have. Okay. Because for example, the materials question that you asked, right? Today we don't have a fab in India. Where, let us say, sir creates a new material. He thinks that this is going to work. Where is he going to go and test that? So one of the things the National Quantum Mission is doing is to create these central facilities where people can go and test out their ideas, okay, new ideas that they have, whether it is hardware, software, all of that, you should be able to go and try that idea out, okay. And that part itself is going to take 2 years, 3 years, 4 years, because we don't have it. Today we don't have it. But we are not very behind either. In the world, how many people have it? Not too many. So great, we are starting now. Okay, so quantum is one area where the ambition matches with the speed and the intent. Okay, so AI, we are a bit late now. We keep talking, acha LLM banayenge, wo banayenge, but it's good, we should do it. But I think in fact, many people lost the AI, even IBM lost it, right? OpenAI was a big surprise for everyone. Now they are all playing catch up, whether it's Google or anybody, right? But the question is, all of these are exponential technologies and we can't foresee the future. So I was just telling in the morning to Shivji that, for example, the founder of internet, did he foresee कि यहाँ Uber होगा, Amazon होगा? None of that was foreseen. None of that. Okay. He foresaw 2-3 examples. Okay, internet will be there. I will be able to communicate with somebody in some distant place. I will be able to share information. That's it. 0.1% of the use cases they had. Okay, that's all he could foresee. He was the founder, the creator, inventor of the World Wide Web, but he could not foresee Uber, Ola, none of the use cases of today. Because once you start a technology, it grows exponentially. We as humans cannot see that far into it because it takes a life of its own. Technology takes a life of its own and it moves faster because everyone gets involved in it. And once that involvement happens, you and I have no control over that. But to keep track with that exponential growth, you need this infrastructure in place. Okay, that's the only way. In semiconductors, today, 𝗏𝗏, we are paying billions of dollars for 10 generations old technology. 10 generations old. Billions of dollars. If we had spent that 1/100th of that amount 30 years ago, today we would be sitting on the table and talking as equals with semiconductor companies to say that, look, I have this, what do you have? And that's what National Quantum Mission enables us. If we play it right, we get a seat on that table. The 5 countries which control the supply chain here, we are not there. And that's why we don't have a seat on the table today. No seat for India. We are trying to get on that table by paying billions of dollars, 𝗏𝗏 बना रहे हैं, वो बना रहे हैं. But it will take us time. But if we had foreseen this 30, 40 years ago and stayed with the trend, we would be somewhere else. And that's exactly what NQM is about.
Thank you very much. So while being part of the NQM, one thing that was very clear is the government didn't want any silo research. They didn't want like exploratory science. Chalo karke dekh lete hain type. It's a mission mode, deliverable based, and the deliverables have to align with the national priorities and so on. So in this, while government is framing the policies and IITs and other academic institutes are doing hardcore R&D, industrial players are coming in. What role like a new institute like ours, like an emerging one, how can we contribute to this national endeavor? Where do you see like through new curriculum development, manpower training, or through incubation, how do you see that new and emerging institutes should come up and place their contribution to this national mission?
Actually, that's a very, very important question because professors by design are not meant to be businessmen. They're a different class of people. They go teach, they do their research, but you tell them इसको market ले जाओ, they have no clue. Okay. And so at some level, it's a hard problem. NQM, though the intent is there कि हम technology बनाएंगे और उसको market तक लेके जाएंगे, but that leaving it just to the professors does not work. It doesn't work. Okay. It has never worked anywhere in the world. The professors, Google भी professors थे, but they started a startup. They were not sitting in Stanford and saying कि मैं professor रहूँगा, but I will do this also. It doesn't work. You need people who jump into startups, start creating industry. The thinking itself has to be different. Okay. But have we created that yet? Not yet. So as NQM, we have given money to the profs, but we haven't created that enablement yet, where we have said, अच्छा, Reliance के साथ जाके काम करो, Jio के साथ काम करो. And that's something you have, a beautiful positioning which you have. So in fact, this morning only we were discussing some of this. Look at IIT Madras. IIT Madras has a brand value. You all know about IIT Madras. But there are two things which IIT Madras has done which is bigger than the IIT itself. Number one, that data science course, online data science course. It brings them more revenue than their regular courses, number one. Several kids in Delhi, I know, they go to Hindu college, Stephen's college, but they also do that data science course. So they had that vision a few years back to create this online program in an emerging technology area, which is now bigger for them than everything else. The second thing that they did was create this IIT Madras Research Park. 4 billion valuation today. Biggest research park in the country. And again, IIT Madras this big, research park this big. And every institute, so you as a new institute, you can jump forward, leap forward. You don't need to go through the 40, 50 years that IIT Madras went through to learn these things. You can do it today. You can just start some courses. You can go and start engaging with the government of India to say that, look, we are an institute, we have an AI course, we are getting into quantum, and here is a vision, because if you look at it, there is Niti Aayog, NASSCOM, all of them are coming out with reports, but who is executing them? You need to be that executor, and to do that, you can't work like the IIT's work, which is where the professor is only the teacher or the researcher. You need to think beyond that. How can we create that research park here? How can we create that online courses here, which creates that brand awareness about Geo Institute? And also, what are those key technologies which you don't have to invest big money. You need to invest big thinking. That's what you need to.
Yeah, thank you. That's insightful, and it's also very true that, let's say, institute, irrespective of, let's say, its name and age, we can still find little ways and make deep inroads into this nationwide endeavor that's going on. From your book, it's very exciting to read. You mentioned about, let's say, the lack of trained professors, that one of the key and issues that even institutes and research labs are facing. That is something that even India needs to address through proper faculty development program and others. That is maybe one of the things you can just elaborate upon, like what's, let's say, the best upscaling model that an institute like ours can follow. And also there are many students joining, and from students there is always some questions, burning questions about job opportunities. And you mentioned how, let's say, without special intervention, in this year itself, 50% of vacancies in US will stay vacant because you don't have trained personnel. Pixel Photonics CEO saying that there is not a single European who can fill some of their positions, and the EU delegate coming to India and say, we want to hire from you. So this presents the students with a golden opportunity. So what are the skill sets, let's say, the students should pick up within the next few years to make them deployable in this, let's say, in emerging quantum technologies that's shaping up, not just in India, but also, let's say, abroad. So if you can touch upon these two things, the faculty upscaling and the skills that students need to really learn hardcore.
So the faculty upskilling, there is, we started a program with MNIT Jaipur, okay, for just faculty FDP programs online, 40 hours of online lectures for 1 month, 2 hours every day with live lectures, okay. And we were amazed, 1,000+ registrations from faculty across India. But the registration to ho jate hain, that's not the problem. But the completion rate, here 80+% of the faculty were actually completing and taking the exams. That's what amazed us, saying that, okay, people usually register, 1-2 hafte baad they go away, they do other things, exam nahi lete. But here people were taking those exams and they were completely engaged throughout, the numbers did not drop. It was 800, 900 people joining every day, okay, that's how it was, okay. So there is lot of interest, okay. Whether you talk about AI or quantum, both of them, and they go hand in hand, in fact, okay. So there is a lot of interest, but as you said, there is a shortage, and we need to think about creative ways in which we can bring these people up to a level where they can start teaching or engaging, right? In terms of students, okay, the example you gave about Europe and all of that, Qiskit is the programming language for quantum, okay? It's the product which people use to engage, program on a computer. That development has come to India. Why? Because of this talent. People who know mathematics and programming. Where are they? They are all in India. People who know maths plus programming. That is a deadly combination. You don't find it anywhere. Maths plus programming, you go search everywhere. Either you have to bring an Indian, give him a visa and bring him there, or you come to India. These are the only two possibilities, okay, at scale. So our kids are already, getting engaged at the right level, but to kids, I would really tell them that become builders, you have to, for example, today, if I say that, let us say an AI course, you have a book in AI, let us say some book, okay? Can your students, so which course do you teach, if I may?
I was teaching linear algebra.
Linear algebra, perfect.
Taking quantum computing this.
Excellent. So let's stick to linear algebra. Okay, so you have maybe 2-3 prescribed books for linear algebra. The student should be able to build a QA system on those 3 books. And the test is, sir gives a test, exam, that model which you make AI should score more than you score. If you score 80% in the exam, your AI model should score 85%. How do you make such a model? You go to YouTube, just like you can make dal lo, ubalo, pani dalo, ye karo, wo karo, you can make a LLM. It could be completely an open source, or it could be APIs like OpenAI. You can make this, okay? So these are the kind of kids that go forward. They are the ones, yes, AI कर देगा, programming भी कर देगा, but it's not going to be able to build this system which I just told you about. And you need to be building these systems, okay? You need to be able to solve real problems around you. Use AI to solve something, build, because bookish knowledge is very deceptive. You might read the linear algebra book and think, मेरे को सब कुछ आता है. But until you actually go and start implementing it and build something out of it, you have not achieved it, okay? So, jobs in most IT companies, AI looks at your resume, we look at your GitHub, we look at how many open source commits you have, how many PRs you have done, what kind of, systems have you built. That's what really matters, because every kid says, I've done whatever, A grade, B grade in my course, I've done AI, I've done linear algebra, I've done these courses. Everyone has done those. So what makes you stand out is that you have taken a book, built a model on top, and made it pass the exam, and made it score more than you can score. That's what every child has to do. And that's what, as teachers, we have to give them that opportunity to create these things, because once you've done that, you can go and solve anything out there.
I think it's very, what we follow here is also very close. We emphasize on project-based learning, not just sit and answer randomly in exams. So we put a lot of stress on projects and give them much weightage. So I think for the sake of time, we have to close it. It was lovely talking to you. I would have wished we could have carried on. There were so many other questions, but let's all thank our speaker here, Dr. Subramaniam, for his insightful discussion.